All right. Good morning. I am trying to get a network because I want to use it. All right. So we are covering this section on graphs. I heard from you that you don't like too much the textbook. So I thought to present some material from the web. Some of you like videos, so I'll run them and we can discuss, see whether the concept go through. This is an experiment, and if it works, I will adopt it more frequently, and if it doesn't work, we'll go back to the style that we had before. Sounds good? All right. What are we doing these days? Talking about graphs. Should I briefly review the concept and the terminology? All right. What is a graph? Very good. You are beginning to learn the language of math. It's a pair. There are two things. One is a set of elements that we call nodes or vertices, or maybe even points. But the nodes and vertices are the most typical. And then there is a set of edges. Edges conceptually represent the connection of two nodes, and we can represent them in a slightly different way depending on the graph. Some graphs are directed. So when we talk about the connection of two nodes, the connection is one way, like a one-way street. In some other cases, two ways. And so depending whether it is one case or another, we can make different choices. If it is both ways, there is not the first point and the second point, so we can put them in a set, because the elements in a set have no order. If there is a direction, we put them in a pair, and we call the first initial and the second final or terminal. And so there we see an example where the nodes are labeled A, B, C, D, and the edges is a line between these two that we call an edge or an arc. And is this directed or undirected? Undirected. If we represent it in this way, there is no preference to go from A to D or D from A. We have a terminology, adjacent node, initial and terminal, incident to or from, and everything else. I'm not going to repeat it, but this is explained very well in the textbook. You can read it there. We saw some properties that always hold in a graph. An edge always connects two points. So if we count how many edges are incident to a node, over all the nodes, we have some constraint. And this sum over all the nodes has to be twice the number of edges. Because this sum has to be even, if for some node this number is odd, there has to be another node for which the number is odd to make the sum even. There is no other way. And so we have the second that the number of odd degree vertices has to be given. And so, if a graph is directed, we make a distinction between the degree of edges going in and the degree of edges or number of edges going out. After this, interesting, we saw the representation of a graph, and we saw three styles. One is adjacency matrix, where the marginal entries, the rows and the columns, represent the nodes, and a 1 in the metric means that they are connected, and a 0 means that they are not. If you have a multi-graph that typically we don't, you can have a count. Yes?
So what is the 2?
Say it again.
What does the 2 mean?
2 means that there are two edges from the very same nodes. Like in this case, from B to C, there is an edge E2 and an edge E3.
So that only makes sense if it's weighted?
No, it only makes sense if it is a multi-graph. So, in a multi-graph, you have many edges. You can have many edges between two nodes. And a practical case is where you have two cities connected by multiple airlines. Yes?
But if those edges were directed, then it would only be 1, right? So it's like...
Well, if they were both directed from B to C, you will have a 2 from B to C and a 0 from C to B. All right, and then we have the incidence matrix, where for every edge we mark which nodes the edge connect. So, for example, looking at that image, you see that the E4 goes from A to D. So, if you look here, E4, you find the 1 in AD because A and D are the nodes that are connected. And finally, we have an adjacency list. For each node, you keep a list of all the nodes that are connected to it. Very simple. Accessing a connection is much easier in a matrix because it's direct access. If you have a list, you have to go over the list hoping to find it out. You could have a tree instead of a list, and the tree can be balanced, can be a binary search tree or other things if you need to do that. All right. Finally, we saw traversals. We skip because we didn't have much time, and we saw traversal. What is a traversal of a graph? A traversal of a graph is the list of the nodes of the graph obtained according to some algorithm. And we saw two algorithms. One we call it a depth first, and the other one we call it breadth first. Depth first means it goes down as much as you can in the graph. When you get to stuck where you cannot go any further, you move back to the last choice you make and you try something else. I found animations for this, and maybe if we have time we can look at this again. Breadth first means you start from one node, and first you list all the ones that are one step away, then all the ones that are 2 steps away and you didn't count yet, then all the ones that are 3 steps away and you didn't count yet, until you are done. To explain is much simpler than the other one. To compute probably is more complicated. When you have to do this by hand, both are relatively simple. So far so good? All right, so now I go back to the place where I stopped. And we talk about isomorphism of graphs. What does it mean, isomorphism? is from the Greek to have the same shape. Better with a light or without? So suppose that I have this graph here. And suppose that I have this graph here. These are the same graph, right? What is the idea that these two are the same graph? Let me call this A, B, C, and D, and this one X, Y, Z, and T. All right? So I can map nodes of one to the nodes of the other one. For example, I can map A to X, B to Y, and this mapping is a bijection. And this mapping has also a property. How do we call this mapping? Let me call this mapping F. If F goes to X, F of A goes to X, and F of B goes to Y, then there is a mapping between edges. Let me use a different color. I use black. This is edge E1, E2, E3, and E4, and this is edge N1, N2, N3, and N4. I have a mapping, let me call this a G, that send E1 in N1, G of E2 in N2, and so on. And this is a bijection. So because they are bijections, the two graphs have the same number of nodes and the same number of edges, right? I want one more property, that if this edge is G, if A1 is an edge from A to B, like it is here, N1 is an edge from F of A to F of B. All right? So this is the key point. N1 is equal to what? G of E1. So basically, G of AB is equal to the pair F of A, F of B. Well, so maybe I should put an extra pair of parentheses here, because the argument is a pair. So thank you for making the notation better. So basically, G preserves the mapping of the nodes. Here we mean F. This is F. F, sorry, my bad handwriting. F and F. Yes?
What if this is like a weighted graph where like E1 is like 3 and N1 is like...
No. E1 is still AB. Then there is a label, but the graph is the same. So here we could even, we have an isomorphism between a weighted graph and a non-weighted graph. When we do this one, we forget the weight. They don't play any role.
Is there a relationship that deal with like a rotation of the graph itself?
Rotation. Yes. So now, let's go back to this example. You see that in this example, when I draw it oops, you don't see anything. You see in this example, when I draw it, two edges cross one over the other. So a graph where edges don't cross over each other is called planar, because you can write it on a plane. So one question is, can you find a planar graph which is isomorphic to this?
Move B down, like near B.
Very good. Very good. So let me write it here. Let me write them both. So this is the original. Thank you. I'll put a 1 as an index because this is the first graph, all right? So how do I represent this one? Basically, I represent it in this way. This is the same graph planar, where I have what? A2. I think this is D2. We have to be careful here. This is B2 and this is C2. And so here I map f of x1 goes to x2, right? What I mean is that A1 goes to A2, B1 goes to B2, C1 goes to C2, and D1 goes to D2. You with me? This is F. Now, we have to make sure that G respects this. So, should we put a name to the edges? Or maybe I'm not going to do it, I just write the edges because otherwise I have too many indices and things get messy. So let's write all the edges. I have A1, D1, A1, C1, B1, D1, B1, C1, and D1, C1. These are my edges, right? So this edge here, let me make it, this is mapped to what? This one. Yeah? Now let me do another one. This one here is mapped to what? The red one. To this one here, right? So now, this works well because A1 maps to A2 and C1 maps to C2. So because there is an edge, I have the function G has to map that edge. And so this one maps to A2, D2, and then this one maps to A2, C2, and here you can verify that all the other ones are respected. Yes? And so, in this way, we say where two graphs have the same shape. We call them isomorphic. And now, because you can look at the graph, at the tree as a graph, we haven't done it much, but certainly you can. Then now you have this notion of isomorphism of trees. And you can say when two trees have the same shape.
Is that what like a spanning tree is?
No. Then we get to the spanning tree. No, if you have two trees, let me write the two trees here. If I have a tree, thank you.
No. Oh, you were just
I need a cameraman here to do all these things. So if we have a tree here, are these isomorphic? Obviously not, because there is not a bijection between the nodes, because one has more nodes and more edges than the other, right? If I draw this one here, are these two isomorphic? Yes, because we can map nodes and edges, so everything works well. Basically, to map it, you look it at a mirror. You put a mirror on one side, and the second is the mirror image of the other. All right, so we have a notion of isomorphism of trees. All right, a little bit more terminology. A path. What do you think is a path in a graph? You start from some node and you cross over edges until you get to some other node. Very intuitive. And so the path is the sequence of nodes that you go over. If you go from node V0 to node V1, you must have an edge there, because if you don't have the edge, you cannot walk. There is no path. If a path starts from one node and go back to the same node, we call it a circuit or a cycle. Circuit and cycle are two words for the same concept. We say that this cycle is simple if you do it only once. You don't go over it more than once. So, should we look at a cycle here? From A, I go to D, to C, and to B. This is a path. I cannot go from A to B to C to D. This is not a path, because there is no edge between A and B. Is there a circuit there? Can you do a circuit? A cycle. A C D A C D A A C D A. This is the cycle. Is this simple? Yes, because you go over the edges only once. What would be one not simple? A C D A C D A. You go over twice. Yes?
What about A, D, B, C, A? Is that considered simple?
Say that again. A.
A, C, D, B, A.
Yes, that's a simple, because you don't cross any edge more than once. All right? And so, these are relatively simple concepts, very intuitive. So, we say that a graph is connected if there is a path between any two nodes. So, can I show you an example of a graph which is not connected? This is a graph that is not connected. Why is not connected? Let's give name to this, A, B, C, and D. Why is not connected? There is no path between A and B. And so this is not connected. Yes, B is isolated. And very sad about it. So now, I don't know how you pronounce this one. In his language was Euler. A lot of people call it Euler, whatever is the name. So here you have a notion of an Euler path and Euler cycle or circle. Here you traverse every arc exactly once.
What's the difference between that and simple? Or is it just because the Euler you have to go to every...
Right, you have to go over each one.
So it's a simple circuit that includes every edge.
It's a simple circuit that includes every edge. Yes? And so, where is this coming from? Supposedly from the birth town of Euler. And so here supposedly is the topography of Königsberg. Königsberg was a city a little bit like Portland with a lot of river and bridges across. And so there were two sides and two islands, like Ross Island Bridge and some other island. And there were those bridges. You see that there are 7 bridges. This is a bridge to go from one side to the island. And once you are in the island, you can come back from this bridge, you can go on the other side with one of the 2 bridges, or even go to the other island. And so the idea is, on a Sunday afternoon, can you start from one point, across every bridge only once, and go back to the same point? You have a circuit in which you traverse every edge only once. I think that no one did it. This was just a joke. Alright, so this is where the name comes from. And this is also, some people consider this where the theory of graphs came about. By the way, I think I said here that I work on a language called Curry, and we run a few programs in this language. So the computation model of Curry, at least once, is just a graph rewrite. In a program, when you have to compute when you have to execute the program, you start with the graph, and you massage a little, and then you massage a little, and then you massage a little, until the point where you can't change anything anymore. And this is the result of the computation. All right, so here we have a theorem. I'll just get rid of this one. We have had the theorem. So you can find an Euler cycle if every node has an even degree. Even degree means that you have a way to enter the node and a way to exit, and then you may come there from a different edge and you enter and exit, and every time you enter, you exit. You may understand this, right? If you have a node, let's say, with 3 edges or 1 edge, once you traverse that one, you are stuck there. You cannot go away anymore, right? And if there are 3, you use 2 to go in and out. And then at the last one, either you start from that one, you end from that one. So if we look at the initial one, is there an Euler cycle for this one? No, because there is a node of degree 3 which is not even. So basically, if you start from D, you can never go back to D across all the edges, right? Is there an Euler path? Not a circuit, a path. Path means you start from one point, you cross over the edges, and you end at some other point, or even that one. Then would be a cycle, but doesn't have to be a cycle. Yes? CAD. Yes. And so you cross all of them. I think there is a game the children play where you represent an envelope. Does this look like an envelope? Yeah. And so here is to find an Euler path. Does it exist? Yes. So you can have at most 2 of odd degree. And if it is odd degree, you have to start in one and end in the other. You see, you have to traverse all these 3. Right, 1, 2, and 3. So 2, you go in and out. And the other one, either you start here or you end here. There is no other way that you can do the other edge. And so here there are 2 of odd degrees, so you must start from one and end to the other. Once you know, this is a big advantage rather than starting someplace, you get stuck. If you don't start from one of these 2 and end in the other, you are not going to find the path. All right? All right, Hamilton path and cycle is a similar concept where you go over, you traverse each node exactly once. So if we go back to the first, do we have it? I think someone said it before, right? A, D, C, B. This is a path. You have a cycle? D, B, C, A, B. That's a cycle. So if you have a graph, to say whether there is a Hamilton path or circuit, this is one of the most computationally intensive problems. Oops, you are not seeing. that you solve with a computer. In fact, if you want to find a problem that is very difficult, you show that is equivalent to this one, and then you give up. A variation of this one that you may know is the traveling salesperson problem. What is the metaphor behind this one? You have a salesperson, and this person has to go over a number of cities trying to sell the product. And so you want to find the connection between cities that gives the shortest distance. Let me make an example here. Suppose that this is a rough map of the United States. Here there is Canada, and here there is Mexico. And suppose that you have two cities here, like New York and DC. And you have two cities here, like Portland and Los Angeles, right? So suppose that the salesperson starts in Portland. One way to do it is to go from Portland to New York, right? From New York to LA, from LA to DC, and from DC back to PDX. Going across the country is really the long distance, right? So you could do better if you go from PDX to New York, from New York to DC, from DC to LA, and from LA to PDX. This is short, right? Yes?
Isn't that required that we have a weighted graph? Because you said you have to
A weighted graph, yes. In this case, yes. And so with the four cities, of course, you can try all the possible combinations, and they are not that many. But if the number gets bigger, it's going to take too long to try all the possible combinations. And so at some point you will study complexity, and there is a class of problems of this kind that they are all equivalent. And no one knows how to solve efficiently. And if you can solve one, you can solve all the other ones. And so the conjecture is that there is no way to solve these efficiently. Otherwise, someone would have been smart enough to solve at least one of these. And if you solve one, you solve all the others. All right. So now we do some. What time is it? Now we do some algorithms. So I'm sure a lot of you use Google Maps to know how to go from one place to another. And typically when you do it, Google Maps give you the shortest way to. Sometimes it's shorter in the distance. Sometimes it's shorter in the time. Particularly during rush hour, they suggest to take another one because it's a little bit longer, but it's going to take less time. How do we compute this? And so this is an algorithm that Dijkstra, very famous mathematician, he wrote a very nice paper in the 60s, I think. He got the Turing Award, which is like the Nobel Prize for computer science. And he defines himself as a humble programmer. He got a degree in theoretical physics. Then he applied for a marriage license in the Netherlands. And he had to write on the marriage license his job, his profession. So he wrote a programmer. And the clerk says, this is not a job. There is no such a job. So we don't take it. And he wrote a theoretical physicist. And so he invented this in a bunch of, he had a degree in theoretical physics. So I guess a theoretical physicist is a good job. There is a famous winemaker down in the Willamette Valley, which is a theoretical physicist, but actually makes a very nice wine. I won't make any name on this. So, here, what is the problem? The problem is we have a graph. I start with this one. You see the graph here? And so the nodes are in red, and the number that you see inside, is just the name of the node. We name it 0, 1, 2, 3, 4. The edges are weighted, undirected, and there is a cost associated. So we're gonna want to go from 0, I guess, to 4, and take the shortest path, the path with the least cost. And for example, you may have the idea that, well, I take a 4 because it's the smallest, but then after 4 you have an 11 and an 8 if you want to get out of 1, right? Which are relatively high. But if you take 8, then to go out from 7 you have only 1, and to go out from 6 you have only 2. So with a small cost you make quite a bit of distance, right? And so now we study the algorithm for finding the shortest path. And I have two versions. One is this one here, where I describe it, and the other one is the version with the movie. So let's see how it works with the movie. Is there any voice here?
In fact, Dijkstra's algorithm will find the shortest path from a given starting vertex to every other vertex in the group. Consider this simple group. Our objective is to find the shortest path from A to every other vertex. Once it is run, Dijkstra's algorithm will generate this information, which includes everything we need to know. We have the shortest total distance from the starting vertex to all of the other vertices. The total shortest distance from A to B is 3. From A to C, it's 7. From A to D, 1. And from A to E, it's 2. We also have the shortest sequence of vertices from A to every other vertex. In other words, the shortest path. For example, to get from A to C, notice that we arrived at C via E. This is shown in the previous vertex column. When we examine the information for E, we can see that we arrived at E via D. And when we examine the information for D, we can see that we arrived at D via F. So the previous vertex column actually gives us the shortest path from A to every other vertex. So how does Dijkstra's algorithm go about generating this information? Dijkstra's shortest path algorithm works as follows. We're using two lists, one to keep track of the vertices that we visited, and another to keep track of the vertices that we haven't visited yet. So let's consider the starting vertex, A. The distance to A from A is 0. That seems rather obvious, but you'll see that becomes important a bit later. The distances to all other vertices from A are unknown. So for the purposes of the algorithm, we're going to set them to a very high value, let's say infinity. We can include this information in our table straight away. Now the algorithm begins good and proper. We'll start by visiting the unvisited vertex with the smallest known distance from the start vertex. First time around, this is the start vertex itself. It's A. For the current vertex, we then examine its unvisited neighbours. Well, we're currently visiting A, and its unvisited neighbours are B and D. These are the vertices that A shares edges with. For the current vertex, we calculate the distance of each neighbour from the start vertex. This may seem like overstating the obvious at the moment, but it will become apparent why we state it like this a little bit later. For now, the distance from A to B is nothing plus 6, which is 6, and from A to D is nothing plus 1, which is 1. If the calculated distance of a vertex is less than the known distance, we can update the shortest distance in our table. Well, at the moment, all of our shortest distances are infinity, so we can update these two distances. Now, we update the previous vertex for each of the updated distances. In this case, we visited B and D via A, so we'll write this information into the previous vertex column. Now, add the current vertex to the list of visited vertices. We won't be visiting A again. Now the algorithm begins to repeat. Visit the unvisited vertex with the smallest known distance from the start vertex. This time around, we can see in the table that it's vertex D. For the current vertex, examine its unvisited neighbours. We're currently visiting D, and its unvisited neighbours are B and E. For the current vertex, calculate the distance of each neighbour from the start vertex. The distance of B from A is the one which we've already written into the table, the distance from A to D, plus another 2, giving us a total distance of 3. The distance from A to E is the distance from A to D, which we've already calculated and written into the table, 1, plus another 1 from D to E, giving us a total distance of 2. If the calculated distance of a vertex is less than the known distance, update the shortest distance. The shortest known distance from A to B, as written in the table, is 6. We just calculated a new shortest distance of 3. The shortest known distance from A to E, as per the table, is infinity. And again, we've calculated a much shorter distance from A to E. So we can write these values into the table, replacing the previous values. We found some shorter paths. Now, we update the previous vertex for each of the updated distances. In this case, we visited B and E via D. So we write this information in the table. Add the current vertex to the list of visited vertices. We won't be visiting D again. And once again, visit the unvisited vertex with the smallest known distance from the start vertex. This time around, the information in the table tells us that it's vertex E. For the current vertex, examine its unvisited neighbours. We're currently visiting E, and its unvisited neighbours are B and C. For the current vertex, calculate the distance of each neighbour from the start vertex. And again, using the information in the table, we can see that the total distance to B is 2 from the table, the distance to E, plus another 2, giving us 4. And we can see that the total distance to C from A is 2, the distance to E from the table, plus another 5, giving us a total of 7. If the calculated distance to the vertex is less than the known distance, update the shortest distance. Well, we don't need to update the distance of B this time. We've calculated 4, but our table indicates that we've already got a shorter path, so we'll leave that alone. On the other hand, the total distance to C that we've just calculated is 7. In the table, it's currently infinity, so obviously we're going to overwrite that. And since we've updated the value for C, we're going to update the previous vertex for C. In this case, we visited C via E. We add the current vertex to the list of visited vertices. We won't be visiting E again. And as before, we visit the unvisited vertex with the smallest known distance from the start vertex. This time around, it's B. For the current vertex, examine its unvisited neighbours. Well, we're currently visiting B, and its only unvisited neighbour is C. For the current vertex, calculate the distance of each neighbour from the start vertex. So performing the same calculation again, we find that our total distance from A to C is 8. If the calculated distance of a vertex is less than the known distance, update the shortest distance. Well, the value in the table for C is currently 7, so we don't need to do this. Update the previous vertex for each of the updated distances. No distances were updated, so we don't need to do this either. Add the current vertex to the list of visited vertices. B won't be visited again. Visit the unvisited vertex with the smallest known distance from the starting vertex. This time around it's C. And for the current vertex, examine its unvisited neighbours. Well, we're currently visiting C, but it doesn't have any unvisited neighbours. There's nothing to do but to add the current vertex to the list of visited vertices. There are no more vertices to visit, so our table of information is complete. Let's just put those steps together into an algorithm. You can see all I've done is rewrite those steps inside a repeat until loop. It's worth pointing out that Dijkstra's shortest path algorithm is an example of a greedy algorithm. And that's because of this step in which we're selecting the next vertex to visit. The algorithm chooses the unvisited vertex with the smallest known distance from the start vertex. The truth is, we could select the next unvisited vertex using pretty much any criteria we like. But the assumption here is that if we select the closest one from the start every time, we will get to the end more quickly. To define a greedy algorithm more succinctly, we say that it makes locally optimal choices at each stage in the hope of finding the global optimum. With some graphs, this greedy approach is desirable, particularly if we want to find the shortest paths from the starting vertex to all of the others. But what if we simply wanted to find the shortest path from A to E in this graph? The short-sighted greedy approach would result in unnecessary processing. Here I've just refined it slightly, but it's essentially the same information. A little bit closer to something that we can implement.
All right, before cancel. I wanted to point out first, is it easy to follow?
Use vertex C. In this case, we visit.
So a few points. This algorithm finds the shortest distance from the origin to every other node in the graph. Not one. Why? Because the cost of finding to one is the same as finding to all of them. So here there is a key point to observe here. At this point we found the distance to C, right? Can we give up at this point and say we are done? Or we should continue the algorithm? Because here we still have 3 unvisited nodes, right? E is done and now it's going to be moved. But should we look at B and C, or there is no point in looking at them?
This path from B to C may be something less.
Fantastic, because the path from B to C, if instead of 5 is 1, we are going to find a better one than the 7 that we have there. We will find the 5. So this is why you have to look at the shortest to every node. All right? Say it again. You like the video? Of course. These are done. This is 10 minutes that probably took 10 hours to do and to prepare. So yes. So if you look there are, I would say there are hundreds probably videos for this. and 100 for a bunch of others. So I looked at a few, and not only for this, and now I have a couple of others for other problems. And one, in my opinion, was completely wrong, so I put it aside. If you go there and look, be critical. Make sure that what they say makes sense. And if you don't like one, you can try another one. Some are much more complicated than this one. And so I prefer simple things, but if you want to see a bigger picture, you can look at the more complicated. All right? So before breaking, as we usually do, let's go back. Here there is the shortest path algorithm in the details that is in the textbook. And this may help you review what we have seen. This is not as good as the one there because this doesn't keep a track, to keep it simple, of the path. We give you just the number of the shortest path. In this one, you have done analytical in words. Personally, I prefer to read it rather than to listen, because when I read it, I can stop, go back 2 lines before. I'm very easy for me to lose the focus. So if I have to go at the speed of the video, I lose it. So here you have another option. Should we say what is this one, shortest path? One more time. So what do we compute here? What do we have and what do we get? Yes?
You have a graph,
I have a graph.
and you compute the shortest distance from each node to each following.
Well, it's good to say. So we have a graph. Is the graph directed or undirected? You can also do it for a directed one. So we have a starting point, and we are computing the shortest distance in the graph from this point to every other point in the graph. There is another algorithm that we don't look here, and it's called Floyd. We're computing the shortest distance from every point to every other point. In some cases, this is what we want. But if you don't, that algorithm is a big O, is n cubed, which is as far as we can go. Above n cubed becomes too time consuming for a real problem. This one is much smaller the complexity. And so this algorithm is computing the shortest distance from some node that you choose, your origin, to every other node in the graph. Of course, when you do with Google, you cannot compute to every other node because there are billions. So there somehow they decide when it's time to give up. Those algorithms are very, very complicated. Far so good? We take a 10 minutes break.